We're going to try to show there's an infinite number of these objects called tau numbers, folks. And tau numbers are just special types of integers that are divisible by the number of their divisors, okay? Now let me talk about this. Well, let's just look at 18. I've listed some of the tau numbers here. We want to show this list is infinite. I'm not telling you it's infinite. We're trying to establish the existence of this ellipsis here, okay? Now there's different letters they use. That we'll use tau. This is supposed to be a tau symbol. It just looks like a lowercase t the way I'm doing it. But tau at 18 is equal to 6. And I'm just saying that, and I'm going to tell you why. It's equal to 6 because there are 6 divisors of 18, namely 1, 2, 3, 6. Oh yeah, we need 9, don't we? 6, 9, and 18. Okay. Again, folks, each of these integers divides the number 18. 1, 2, 3, and this is all of them. And there are 1, 2, 3, 4, 5, 6 of them. Now, another way to do this that's very convenient is to consider the prime factorization of this. In other words, let's say t of, what is this? This is equal to 2. I'm going to put 2 to the first power times 3 squared, right? 2 times 9 is 18, right? Now, another way to do this, and that the proof is very easy, I won't state the proof, is just to increment each of these exponents. See, increment 1 by 1 and you get 2. Increment 2 by 1 and you get 3, and so you get 2 times 3 is equal to 6. And so that's a very nice result. If you wonder why you have to increment, you have to allow for an exponent of 0, since 1 is a divisor of 2, right? And that's just the nature of the proof. It's a very simple combinatorics proof that you just increment each of these exponents. 1 got incremented to be 2, 2 got incremented to be 3, and you take the product. It's what they call a multiplicative numerical function, okay? So that turns out to be useful because it's consistent with this definition here of what a tau number actually is. Notice that in this is the definition of a tau number. Any natural number is a tau number provided the number of n's divisors is a divisor of n itself, okay? Well, we can see clearly that t of 18 is a divisor of 18, and we'll use this vertical bar notation. Okay, t of 18 divides n. That's clear. 6 divides 18, no doubt about that. Okay, now remember we're trying to prove there's an infinite number. Okay, we're trying to prove there's an infinite number of tau numbers, and there's a cool little result here that I came up with, and it was motivated by some stuff I read in other books. I just didn't come up with it off the top of my head. But the claim is that 180p is a tau number whenever p is greater than 5. Now, of course, y'all, p is prime, right? P is some prime number. P is a prime number. Now, let's take a look at this a little more carefully, okay? So, t at, and y'all, just to give you some insight why we're doing this, if we can prove this, well, we're done, because a corollary to this is there's an infinite number of tau numbers since there's an infinite number of primes greater than 5, right? So once we prove the claim, we're effectively done with the proof here. Now, so t at 180p, t evaluated at 180 times p, where p is a prime greater than 5, okay, this is equal to tau. I keep calling it t, tau. Tau is getting used in 2 ways. It's getting used as a definition and as an operator. But we can write this 180 is equal to 36 times 5. Well, that's 2 squared times 3 squared times 5, right? 2 squared is certainly 4. 3 squared is certainly 9. 4 times 9 is 36. 36 times 5 is 180. Okay. Now notice also we got to juxtapose the p there. Okay, but what do we know? We've already seen the pattern that occurs when you're finding the divisors. You increment each of the exponents, right? And so notice that this is equal to, let's increment 2, we get 3. Let's increment this 2, we get 3. Now notice 5 is a prime number, and we'll say to the first power. So we get a 2 there. P is a prime number, of course, with an understood but superfluous exponent of 1. So that'll give you 2, right? But what is this equal to, folks? This is 9 times 18. That's equal to 36, right? I'm sorry, 9 times 4 is 36, right? Okay, so it's clear that 36 is a divisor just of 180, right? So what we've shown is that we've just shown that T of 180p okay, being equal to 36 is a divisor of 180p, right? Pretty cool, folks. Again, because this is equal to 36, right? This object, this entire object, the result of this operation is 36, and 36 is a divisor of 180, making it a divisor of 180p, right? So that's the claim has been proven, and also I can write QED to the overall claim that the primes are infinite. Since the primes are infinite, the tau numbers are infinite, right? So QED, tau numbers, such a hassle to write all this out, but the tau numbers are infinite. Grossly abbreviated here. All right, folks, that does it. Hope you enjoyed that. Tau numbers, there's a lot of interesting properties of them. There's some questions about the density of them compared to the prime numbers. This is another interesting thing right here, 9 and 225. They're tau numbers, but notice they're the only odd tau numbers in this list. And it turns out there's a fairly easy result to prove that says that if T is an odd tau number, then, if N is an odd tau number, then N is also an odd square, an odd perfect square, but the converse isn't true. Notice that 169 is an odd perfect square, right? 169 is an odd perfect square, but it's not a tau number, and you guys can verify that, right? So in other words, again, the statement is if N is an odd tau number, then N is going to be a perfect square, and these two examples suggest that that's true. But notice that 169 is an odd perfect square, which is not a tau number. So it's one of those standard A implies B, but B does not imply A. So anyway, that's another proof, and that's a separate video, I suppose. But in any event, we've proved what we set out to prove. Again, thank you for viewing.